So our first speaker in the session, welcome back from lunch. Our first speaker is Stella, and she will talk about whether path induction needs justification.
Yeah, thank you for the introduction, and just want to acknowledge that I received funding from University of California, Irvine and University of Vienna, so I can actually speak here today. So this talk is on one hand, it's like a philosophy talk with mathematical sprinkles, or mathematics talk with philosophical sprinkles, however you want to take it, but I'm coming from philosophy, looking at mathematics. So some philosophical background is that there's a paper by Ladyman and Fresnel who argue that path induction should be justified because homotopy type theory ought to be an autonomous foundation of mathematics, and definitions in homotopy type theory ought to be justified from free mathematical concepts. So they argue that path induction should be justified from free mathematical concept of identity. On the other hand, there's another philosophy paper by Patrick Walsh that he argues that yes, path induction should be justified, and it's an identity elimination rule in sort of type theory. So the justification could be to show that it's harmonious from the identity introduction rule. But I like to question, does path induction actually need a justification? Because these philosophers seem to assume that it does, and they're trying to provide a justification, but I'm not really sure that it does. So my approach, which is different from what Fresnel and Ladyman and Fresnel have said, and it's also different from what Patrick Walsh has said, I'd like to take a Husserlian approach, or I'd like to call it a Husserlian approach. So Edmund Husserl was a mathematician, got his PhD in mathematics at the University of Vienna before he became a philosopher, but part of his philosophical work was developing this method to study mathematical practice or scientific practice more broadly. So he says that we need to enter the community of empathy with the mathematicians. Without going into too much details about the philosophy, what I understand by this is that we need to look at mathematics from the perspective of the mathematicians, of the mathematical community, while understanding what motivated the mathematicians to practice their subject in such a way. So I have three goals for this talk. So one is to explain the perspective of homotopy type theory community, or what I understand to be the perspective. And so what I'll argue for is that there is the homotopical or topological interpretations of homotopy type theory, and that's supposed to be the perspective of the community. And given that path induction is basically what follows from path lifting property from the topological interpretation, so I'm actually going to prove that path induction follows from path lifting property. And so I conclude that we don't really need a justification that's pre-mathematical or harmonious to the introduction rule for path induction. So here's the structure of my talk. I'm going to introduce the perspective, and I'm going to give a quick overview of what path induction is, just to remind everyone, and I'm going to provide the proof that path induction follows from path. So homotopy type theory, as probably most of you will know, is often characterized as an extension of Martin-Löf type theory with the univalence axiom and high inductive types. But I think what this means for the community is that it's a new conception of foundations of mathematics with intrinsic homotopical content and convenient machine implementations, which can serve as a practical aid to the working mathematician. So this is a quote from the book by the univalence foundations. So the intrinsic homotopical content is what's sort of being provided from this high inductive types, and the convenient machine implementation is what comes from using Martin-Löf type theory as its formal syntax. And univalent axiom is what brings them together. So informally, univalent axiom is described as equivalence is equivalent to identity. But in the context of homotopy type theory, they claim that the following statements are equivalent. So if we are given this judgment, P is the term of the type A equals B, then we can have the logical interpretation, which will say that P is a logical proof of the proposition A equals B, or A is identical to B. Or we can have the topological interpretation, which says P is a topological path with the starting point A and the end point B. Or we can have the homotopical interpretation, where P is a homotopy equivalent between topological spaces A and B. And I think that these interpretations are taken to be equivalent in homotopy type theory, and that's what it means for homotopy type theory to be a foundation as they describe it. So just a quick prelude. So we have universe U where every type occurs. So we're going to have, if we're saying A is a type, then we can write it as A is a term of type U universe. And we can say that given a type A and the term that occurs in the type A, there is a term refl A, which is in A identity A. So it can be logically interpreted. It's like a proof that reflexivity of identity holds for the term A in the type A. But also, if you think of it topologically, it could be a reflexive path in the path space. So collection of paths from point A to point A. And then we can describe the identity type on A as this pi type. So logically interpreted, you can read it as x for any x and y in type A, x is equal to y, and that's a type on its own. Or topologically interpreted, you can take it as the product of path spaces. So there are two ways of visualize this. So if you take the left diagram, you can think of that as the space of paths going from point X to point Y. So the point P in that space would be the path going from X to Y, or you can think of it as P is a path going from point X to point Y in the space A. So what is path induction? This is how it's stated in the book precisely. So they say that let A be a type and C be a family of types. So it's going from the identity type to the universe. And they say let the function little c be such that c of little x is a term in the type c xx reflex. So it takes a term in the type A and it gives you the term in this the family of type that we have. Then path induction continues to say that then there is a function f that takes x, y in A and p in x identity y to c x, y, p, such that fxx reflex is little c of x. So the term c, which was defined on the previous slide, basically identifies sort of not in the type, but kind of meta-theoretically what fxx reflex means. So if we take this homotopical topological perspective of homotopy type theory, we can interpret path induction in this way. So we can say, given a space A, let C be a predicate, so that's now the logical interpretation, that takes any 2 points in A and a path between them. We're given that for any point X in A, we have a proof Cx of the statement Cxx reflex. Then there is a function f taking any 2 points x, y in A and the path between x and y to a proof fxyp of Cxyp, such that fxx reflex is C of x. So what's happening, as I understand it, is that C of x, which is a proof of the statement Cxx reflex, is given, and path induction tells us that we can have a function f that generalizes this. So on the left-hand side, we see, so fix a point A in type A, and you're going to have the refl A, which is a path, reflexive path going from A to A. Then CA, which is given, is going to be a point in this space CA refl A. But what happens with the function f is that we can start with an arbitrary path P going from X to Y, and we can basically visualize it in the same way topologically. So to clarify a bit more what this topological homotopical interpretation means is that it allows us to treat identities as paths, identity types as path spaces, and type families as vibrations. So this is exactly what is stated in the book. They say that we think of a type family P, A to U, as a vibration with base space A, with P of X being a divisor over X, and with the sigma XA, PX being the total space of the vibration, with the first projection going from the sigma space to A. So the defining property of a fibration is that given a path P from X to Y in the base space A and the point U in PX is the fiber over X, we may lift the path P to a path in the total space starting at U. And this lifting can be done continuously. That's what's stated in the book. So I'd like to sort of visualize it in this way. So we have the total space sigma X A PX and the base space A, and we have the first projection map. And if we have a path going from A to B, that path gets lifted because we have a point U in PA that's going to be projected down to A, and the path P gets lifted this way. So that's what how they think type families should be interpreted with the topological and homotopical interpretation. So just a reminder of what path lifting property is in topology. So let A be a topological space with a point A, and let P be a path such that the starting point is little a. So then given a map pi, which is kind of a projection map going from C tilde to A, such that there is a point A tilde that's already in C tilde, and that point gets projected by pi to A. And we say that pi has the path lifting property with respect to the path P, just in case there is a path P tilde in C tilde such that the whole path gets projected to the path P. So we can generalize this definition to apply to arbitrary paths, then we can just talk about this projection map pi being having the path lifting property. So what happens here is that we say that pi, the map that projects this lifted path P tilde, has path lifting property. So now, then my results shows that path lifting, path induction actually follows from path lifting. So in that sense, if we take the topological and homotopical interpretation seriously, we don't really need the further philosophical justification for path induction. We can just think of path induction to be satisfying, like we're talking about certain mathematical structures that satisfies this path lifting property from topology. So I'm going to start the proof with the given conditions of path induction. So let A be a type, C be a family of type going from identity to the universe, such that there is a function little c such that Cx is big C is in the type Cxx reference. Then according to the homotopical topological interpretations, the type family is interpreted as a fibration. So we can take the identity type as the base space and the sigma space, which is actually pi in x, y, and a, sigma p in x equals y, cxp, c, x, y, p as the total space. And that's going to look like something like this. We're going to have the base space, which is the identity type, and the sigma space with the projection map. And if we fix a point little a in the type big A, then the reflective path A is given, and we can identify this point referring CA in our total space. But we can also just focus on the second projection and look at the pi type on the right. So we can define the little c, which is given in path induction, as taking up the point A in the space A into this total space that we have above. So now I'm going to define a map pi that goes from the second projection to A, such that pi of C of A is equal to A, and that it satisfies path lifting property. So what happens is that the pi projection is going to be basically an inverse of the map C. So if we take an arbitrary path Q from, say, point A to point B in the space A, then there is a path Q tilde with the starting point that's identified by C of A. So the diagram shows that if we take the reflexive path on A, then that's going to be lifted up to the reflexive path on C of A. But if we have an arbitrary path Q going from A to B, then it's going to be lifted to Q tilde with the starting point at CA. Then how I want to define path induction is that we define the function f such that that f x, y, p is the endpoint of the lifted path p in the space, in the total space. So it's going to be p tilde, so lifted path with the starting point cx. So yeah, so that's the endpoint of the path. And then obviously FAA REFLA is equal to CA, since REFLA is lifted to REFL CA, thus path induction follows. So, so my argument here is that the perspective from the homotopic type theory community shows that we should take the topological and homotopical interpretations seriously. And and especially when we're looking at path induction, we should take that seriously. So mathematically speaking, if you want an argument to show why path induction is a reasonable definition, it's because we're really talking about certain structures that satisfy path lifting property, and we can have this projection map. So if we do so, then path induction holds. So I don't think path induction needs the kind of justifications that other philosophers have argued for. Thank you.
Thanks, Stella. Okay, Fox.
Yeah, I completely disagree. I think homotopic type theory is a bad name, and I thought so at the time. And really, it was Wygotsky's idea was, I mean, inspired by reasoning principles coming from homotopy theory that you can apply into mathematics in general. And the fact that it's a topological model of type theory doesn't tell us anything. So I mean, and I think, I mean, when you explain type theory, homotopy type theory, or type theory, I would say, to people, I don't have to explain them first topology, or I mean, I can explain them as was indicated, the naive idea of these concepts. And path induction is indeed a way to make precise what we mean by equality in a more general sense. I mean, equality in a classical sense, equality is just an equivalent relation which is preserved for a function. But once we give up this idea that everything that equality was a proposition, we get to a more general idea of what we mean by equality, which is a higher group of it. Higher group of it can be exactly classified by equality types as path induction. And I think that's the core of the idea. It has nothing to do with the fact that there's topology, that there's a topological model of it is it's an interesting reuse of mathematics, but it's not fundamental in any sense.
Okay, so could I ask a follow-up, like clarification from you? So obviously you're one of the contributors to the theory itself. So is the omega groupoid structure not? So you think? Are you thinking of the omega groupoid structure independently of the intrinsic homotopical context that's being described in the book?
Yes, I mean, okay, this is one way to understanding it by using homotopy theory. That's fair enough. But the way naively I think about it is that every type comes with elements, but also with an equality type. And to understand what I mean by equality type is more general setting, I have to go beyond the sort of, as I say, classical conception of equality and come up with a more general idea. This is just what we identified in types. It's equality.
It's equality. So is that like, I mean, I'm a philosopher, right? I'm not technically speaking, I'm not a homotopy type theorist. So I'd like to learn from homotopy type theorists. So is what you're thinking more like the sort of the inductive types? Generally, no. Okay.
But
just equality means this particular path induction is just a definition of equality.
They make precise what you mean by equality.
Okay.
Okay, maybe let's have one more quick question, Alex, please.
So I was going to ask, so path induction is obviously part of the type group, but it also has the very existent NLTT just by itself. So do you think, so I guess my question is, why should we take the topological sort of justification when path induction exists separately in an existing situation where the topological interpretation doesn't work, for example, if you have unique things like this.
So does the topological interpretation not I mean, isn't it the assumption of the homotopy type theorists that you will have the topological
Right, I'm
interpretation?
saying half induction exists in settings that are not homotopy.
I see. Yeah, so my understanding is what makes homotopy type theory, as opposed to say just Martin-Left type theory, is the topological homotopy interpretation. So in that sense, this is why I'm privileging the topological understanding, but I'm not. So I think what Ladyman and Fresnel and Patrick Walsh are doing, I think they're more invested in probably what motivated Martin-Left type theorists, and I'm completely open to their project. I just don't think, from my understanding, it's about path induction. Yeah.
Thank you.
Thank you. Okay, so let's thank Stella again for her talk.